Well, welcome back to our lessons, everyone. This is Mrs. Hanson. We're continuing our work in Chapter 11, Introducing Organic Chemistry. We're up to Section 11.3. We're on page 4 of our note pack called Shapes of Organic Molecules. This is going to review what we refer to as the Vesper Theory. Remember that Vesper stands for the valence, shell, electron, pair, repulsion theory. And really what it's telling us is that the most stable arrangement for atoms around a central atom is to be as far apart from each other as possible to maximize bond angles. And so when we look at the Vesper theory, the 3D, the three-dimensional arrangement of atoms around a central atom, the guiding factor is to maximize our bond angles. So an atom that's surrounding by two groups is said to have a molecular geometry of linear, and its bond angle is 180 degrees, as you would expect a straight line to have. An example would be the acetylene. Acetylene contains a triple bond between our carbons. The bond angle between the two carbons, as well as between each carbon and hydrogen coming out, is exactly 180 degrees. So if we have a straight line, the molecular geometry is known as linear. And in your note pack, you're drawing in a line diagram for the acetylene molecule. Notice its triple bond leading out with 180 degrees. In this case, each terminal hydrogen is represented. In a second molecular shape, we look at an atom that is surrounded by three groups. For example, if I change over, let's say, to a highlighter here quickly, notice I have a carbon that is surrounded by three groups. And what I mean by group is we have a double bond leading to a group of carbon. We have a single bond leading to hydrogen and a single bond leading to another hydrogen. The carbon highlighted in yellow is surrounded by three atoms. It has a molecular geometry known as trigonal planar, which means it truly lines up like an equilateral triangle. The three attachments to that central atom being carbon, all lead out to an equilateral triangle, giving it a molecular geometry of 120 degrees around all parts of that triangle. And the same could be true if we highlighted this central carbon. It is surrounded by three attachments. I'll highlight in green. The highlighted three attachments gives us an equilateral triangle. That equilateral triangle gives us bond angles of 120 degrees in each direction. So when I have a carbon bonded to a double bonded carbon, C double bond C, the molecular geometry is now trigonal planar, lying flat in a plane. An atom that is surrounded by four groups is known as tetrahedral, and it has a bond angle of 109.5. So when we refer to a central atom, such as this carbon, and we highlight the attachments, those four attachments being hydrogen in an example of methane, each one of those attachments then, for the molecular compound CH4, has a bond angle of 109.5. Notice it's very different. If we've been drawing methane, such as this, where we might be fooled into thinking that this is a 90-degree bond angle. And clearly we see it's not, because the Vesper theory tells us we want to maximize angles between all atoms around that central atom carbon. And so instead really of having 90 degrees, it's better to draw kind of like a base of a pyramid where all of those lines attach back and one coming up from it. So we're maximizing bond angles where these hydrogens are kind of sitting on a tabletop, Carbon kind of up in the center, and peaking up high would be the top of the pyramid with a hydrogen. This is known as tetrahedral, and it has a bond angle of 109.5. When we look at three-dimensional structures, we try to draw the best we can a 3D structure on a flat page. We do so using solid lines for all bonds that lie in the same plane as your paper. We use a wedge to represent bonds that are in front of the paper, and a dashed line to represent any line that goes into the paper, so behind the plane. And here we have an example of that very structure. The methane molecule we drew just a moment ago, methane drawn just a previous page where we had all single bonds, kind of drawing in a fashion where we had all straight lines. Better than that, to give you an idea of the configuration in a three-dimensional sense, is to use the dashes and the wedges. A dashed line is telling us that that's going behind the page. This is coming directly out at you as a wedge. And if you see a solid line, those are exactly on the same plane as the paper itself. Notice that carbon, which has 4 bonds, the carbon is going to be in the plane of the paper. 2 bonds will always be a solid line, and they'll always line in the same plane as the carbon. 1 will be a dash, and 1 will be a wedge. And you can count on that kind of construction. So every carbon with 4 single bonds is called tetrahedral, And this particular paper is saying that we can draw those, let's say, in terms of any atom coming out. 3 of the bonds will always be in the same plane. 1 of the bonds will always come out as a wedge. And 1 of the bonds will always come out as a dash. And it absolutely doesn't matter where you select to put the wedge or the dash, knowing that that's just a free rotation in space. So I could equally draw this with 2 of the bonds being in the same plane, 1 dash, 1 wedge, and it just doesn't matter where I select those, because it's just an angle of your eye as you're looking down at the molecule. Ethane, with its 2 carbons and 6 hydrogens to complete the octet, when it's drawn in a 3-dimensional shape, notice that the carbons are always placed in the same plane. So that's a critical part, is you always create a solid line between the carbon backbone. The carbons will lie in the same plane. So that means 1 more bond of each carbon has to lie in the same plane. And then the additional bonds will be the wedge coming out of the plane and the dash going behind the plane. And so when we look at, for example, a simple molecule called ethane, notice that. And again, the criteria is the same. The carbons each have 2 bonds that are coming on the same plane as the paper. You see each carbon with 1 dash, and each carbon with 1 wedge. That's the criteria as we learn to draw these 3-dimensional structures. And this is giving us an example of ethane. Critical component is to remember that the carbons have to lie in the same plane. These shapes of organic molecules continue with examining further molecular geometry of a tetrahedral 4-domain group. Suppose of those 4 domains, only 3 lead to atoms and 1 leads to a lone pair. Now, just a moment ago, we said if all 4 were bonded to atoms, we had a tetrahedral shape. That tetrahedral, just to kind of keep in mind, 4 atoms. Here we have 4 domains, but one of those is now leading to a pair of lone pair electrons. So we have a different molecular geometry. The nitrogen, for example, with its lone pair, doesn't have any atom up above here, so now it's referred to as trigonal pyramid. The lone pair of electrons, remember for nitrogen requires 3 bonds and 1 lone pair of electrons. So it would make no sense to call nitrogen a tetrahedral because you need 4 points to make a tetrahedron. You need 3 points to make a trigonal pyramid, and that's the name of our molecular geometry when we have 3 atoms and 1 lone pair. This particular carbon would be tetrahedral. Its bond angles would be 109.5. This particular group right here is called trigonal pyramid. And that means that it's got a little bit less of a bond angle simply because I'm going to say about what they're saying is about 107, just a little bit smaller because these electrons, this big cloud of electrons, actually take more space than an atom would, and therefore kind of reduces the bond angles between the hydrogens, kind of shoving them down a little bit. So 3 atoms and 1 lone pair is known as trigonal pyramid. A next geometric shape to consider around the central atom. If you see 2 atoms and 2 lone pairs, the molecule is now considered to be bent. 2 corners of the tetrahedron and 2 electron pairs give us a bent molecule. For example, water is a bent molecule. Water, with its central atom of oxygen and 2 lone pair, each leading out single bond hydrogens, gives us a bent shape. And the bond angles, again, because these are very large electron clouds, kind of push together those hydrogens, they're reduced to about 104.5 for the bond angle between them. So 2 corners, 2 electron pairs give us a bent molecular shape. This carbon is attached to 4 other objects, 4 other atoms, so it's considered to be tetrahedral. This oxygen is bonded to 2 other atoms. It's considered to be bent with the 2 atoms and 2 pairs of oxygens, 2 pairs of electrons. So thinking about, looking at the geometric shape, the bent part of the molecule, the OH part here at the end, the alcohol group, as we're learning, that's called the functional group of an alcohol, which has bent geometry. So here is kind of one slide to put it all together for us, and we're looking at filling this in together. Table 11.1, the molecular shapes around atoms in organic compounds. I tell you the number of electron domains, and that in my grid, total number of groups, I call an electron domain. So if I'm standing at the central atom and I'm looking out, what do I see? An electron domain is a bond or a pair of electrons. The bond, I don't care if it's single, double, or triple. It's leading to an atom. Okay, so an electron domain can be an atom or a pair of electrons. If I have 2 electron domains and both are bonded, we said that we have linear geometry. The bond angle is 180 degrees. So really, to draw in your geometry, you're just placing a central atom and just drawing straight across and reminding yourself that's 180 degrees. If we have 3 groups around the central atom and all 3 are bonded, we represented that as a trigonal planar geometry. So we're kind of drawing in that equilateral triangle and reminding us that that's 120 degrees in all directions. Planar means it lies flat on the table. If we have 4 domains and all 4 are bonded, we call that tetrahedral. Our central atom leads out to 4 different atoms, and each bond angle is approximately 109.5 degrees. If those 4 domains only lead to 3 atoms and one is unbonded as a lone pair, we called it trigonal pyramidal. Ammonia was an example where the nitrogen in the center led to 3 hydrogens, but this lone pair occupied a great deal of space. So it says approximately 109.5, but remember the bond angle is actually smaller than that. It's about 107 degrees as the hydrogens get kind of pushed together because of the large electron cloud. And the last one we examined, excuse me, 4 domains, but only 2 lead to atoms and 2 lead to lone pairs. This was our example of a water molecule. The water molecule is considered to be bent with approximately 109.5. Remember, these large electron domains end up kind of pushing the hydrogens together. We said it's about 104.5 degrees. So that's why you see the term approximately, as bond angles shift a little bit smaller with an increasing number of lone pairs around that central atom. You might need to pause your video and kind of finish up your grid, giving the shapes, the geometry, and the approximate bond angles. And you're working, of course, to memorize the shapes of these molecules. So this is something you're going to have to practice and commit to memory. That shape around the atom, just to review, these are the things that you've drawn. You drew in a linear shape with 180 degrees. Carbon dioxide would be an example of a linear shape. The central carbon atom leading out to 2 oxygen atoms is an example of a linear molecule. Boron trifluoride would be an example of a trigonal planar molecule. That central atom of boron leading out to 3 atoms. It is trigonal planar. The bond angle between those fluorines is 120. Methane would be an example of a tetrahedral molecule. Methane, of course, with its 4 bonds. One of them would be dash, one would be wedge. You kind of remember that. And as the tetrahedral, 109.5 would be an example here. If instead of leading out to 4 atoms, it only led to 3 atoms and had a lone pair, the bond angle is reduced to approximately 107. And we said nitrogen is very important for this particular example because nitrogen will always have 1 lone pair. And then a bent molecule, such as a water molecule, with its bond angles of about 104.5, a little less than ideal because of those lone pair electrons. Now we repeat ourselves as we're trying to practice to memorize. So let's work on that very thing. Determine the shape around each carbon and oxygen atom in dimethyl ether. Pause the video and see if you can do these from memory yet. And if not, it's okay to peek because we're still practicing. But pause and label the geometry around the carbons and the oxygen. And just start the video when you want to check your work. Okay, well, welcome back. Here we see a carbon, and this is the exact same carbon over here. Both carbons are attached to 3 hydrogens, leading to an oxygen. So what I notice is that the carbon is bonded to 4 atoms, giving us a tetrahedral molecular geometry. And the molecular geometry of tetrahedral has a bond angle of approximately 109.5. Here, the oxygens, remember that's for both carbons. In the oxygen, even though they're not drawn, we know they're there because oxygen requires an octet. It requires 2 bonds and 2 lone pairs. Here I see 2 bonds and 2 lone pairs, telling me that we have a bent molecular geometry. Bond angle is less than ideal, so it's less than 109.5, less than 109, and it's approximately 104. Just a little bit smaller than the ideal 109 degrees. How'd you do? Well, here's some more practice. Pause the video and keep working on these and come back when you're ready to check. All right, so here we're looking at the shape of the indicated atoms in each compound. So as we number these, don't forget to add the electron pairs to any heteroatoms before determining the shape. So if needed, we have to, for example, the bromine is missing its 3 sets of electrons to complete its octet. Notice carbon number 1 is attached to 3, I'm going to just label that carbon 1. That's the first indicated carbon we're to label. It's attached to 3 bonds and no lone pairs. Obviously, carbon will never have lone pairs. So 3 bonds. One of them is a double bond. One of them is a single. One of them is a single, but it's still 3 domains. And if you find that easier to just think about what it's leading to 3 atoms. No lone pair leading to 3 atoms is called trigonal planar. And so drawn correctly, it would have these bond angles that look like an equilateral triangle. This hydrogen then would also be coming out as trigonal planar for carbon 2 because it's also bonded to 3 domains. So looking at the geometry drawn correctly for that structure A, we have trigonal pyramid on carbon 1 and trigonal pyramid on carbon 2, since both carbons are attached to 3 atoms. Let's look at letter B. The first of our carbons is attached to 2 other atoms. So 2 atoms gives us a linear molecular geometry. Bond angle there is 180 degrees. So between carbon 1 and 2 and between the carbon and hydrogen are all 180 degrees. Carbon 1 is linear. The second that we're looking at, labeled here, I notice that that carbon is attached to 4 other atoms. So in structure 2 here for this carbon, since it has 4 atoms, we would call that tetrahedral. So this bond angle on the carbon, being that it's tetrahedral, would be about 109 degrees. This oxygen is missing its electron, so be sure to add the 2 sets of pairs there. And then you can see that the oxygen, which is the 3rd structure we're to label there, is bonded to 2 atoms, 2 lone pair, giving us a bent molecular geometry. 2 lone pair. And so this right here is considered to be bent, and its geometry would be about 104.5 degrees for the bond angle. Carbon 1 down here, it is bonded to 3 different atoms, so we would call that trigonal planar. This oxygen with 2 bonds, 2 sets of lone pairs, is bent. And the last one we'll check together, letter D, carbon indicated as number 1 is leading to 3 different atoms, 3 different domains. So this is trigonal planar. Let's see, the second one here is leading to 2 different atoms, so you wrote out that this is linear. Are you doing well? Keep practicing enough to where you have these memorized. This time, and these are just sample homework questions, is where I'm pulling them. So as we go on, we're turning over to page 8. Indicate the bond angles for each compound. And again, I encourage you to stop the video, work these through, and then come back to check. So with our first letter A, we're looking at the bond angle between those two fluorines. Very misleading because it looks like it's 90 degrees, but we understand it's not. The central atom here is carbon, and carbon is attached to 4 atoms. Knowing that that makes it a tetrahedral molecular geometry, so the bond angle is 109 degrees. So right here, this is approximately 109 degrees. The same is true for this carbon. It's also attached to 4 other atoms, and so that right there is also 109 degrees. It is also tetrahedral. And this, again, this atom between chlorine and bromine, or this atom here between the hydrogen and the other carbon, they all represent 4 atoms, so they're all 109 degree bond angles within that entire structure. So the carbons would lie in the same plane. One of the bonds also needs to be in the same plane, so I can just select, let's say, the chlorine and the fluorine, remembering that one of the bonds then has to be a dash and one has to be a wedge. Here we could have this one leading to bromine and this one then leading to hydrogen. HBrCl on this particular carbon I'll call number 2, and this particular carbon I'll call number 1, but every single bond angle in there is 109. Since they're all bonded to 4 atoms, they're called tetrahedral for molecular geometry. Letter B. Here we have a carbon attached to 4 atoms, therefore it's tetrahedral. That bond angle is 109 degrees. This carbon is attached to just 3 other atoms, so it's called trigonal planar, which is 120 degrees. This carbon is attached to 3 other atoms, so it's also trigonal planar, which makes it 120 degrees. And down here, letter C, our first indicated bond angle is around this carbon, which is attached to 3 other atoms, making it trigonal planar, which lies 120 degrees. The same is true for right here. This carbon is attached to this carbon is attached to 2 other carbons, but also an H. So I was trying to say, so it's attached to 3 different atoms, making it trigonal planar, which is 120 degrees. Remember, this oxygen requires a set of lone pairs to complete its octet. So here you have 2 different atoms. It's bonded to 2 different atoms, but it also has 2 sets of lone pair, making it bent, which means it's about 104.5, a little less than that ideal angle of 109. So as you continue to practice, you're working at, looking to memorize and giving yourself enough practices so you don't need that Vesper chart. Top of page 9, we're going to practice using dashes and wedges. So pause the video and see if you can remember how to draw using dashes and wedges, compound A and B, and then start the video up again when you want to compare your work. All right, well, let's try them. The first is a simple hydrocarbon. Remember that carbon requires 2 bonds that are in the same plane. One will be a wedge and the other will be a dash. So I just selected the carbon in the center. I'll make each hydrogen in the same plane, 1 more hydrogen as a dash, and the chlorine as the hydrogen as a wedge and the chlorine as a dash. It is absolutely fine to select any of these and make them dashes or wedges. There is no one correct answer. So I can make chlorine in the same plane. I can make chlorine turn into the wedge, or I can make it into the dash. They're all the same correct answer. And that's just spinning the molecule in space. You can spin that and view it from any angle and be correct. When we draw a carbon backbone, we want to draw the carbon in the same plane. So one carbon connecting to the next with a solid line. One more solid line for each of these carbons. One will need to be a wedge and one will need to be a dash. And remember, they can go in either order. You can switch around dashes and wedges. What's just important is that we have one of each. And so hydrogen coming out of the plane, hydrogen going behind the plane, and over here I need a bromine and a hydrogen. Remember, this single bond can twist in space. It's free to twist, so it's absolutely okay to just make any arrangement. What's critical is we have, for each carbon, it requires 2 bonds that are in the same plane. One be a dash, one be a wedge. L-DOPA is a drug used to treat Parkinson's. Give the shape around each indicated atom. Are you ready to try without looking up anything from your Vesper chart? Pause the video, give it some time, write down answers to each arrow, and then let's check together. All right, well, we'll start at the top. I'll just place a circle around this carbon. I can see that it's attached to 3 different atoms, making this carbon trigonal planar. This carbon is attached to 4 different atoms, so it is tetrahedral. This carbon is attached to 3 other atoms. That's trigonal planar. This nitrogen is missing its dots. You didn't fall for that, did you? So 3 are bonded, 1 pair of lone electrons. This is called Trigonal Pyramid. We have another arrow right here on the oxygen. Don't forget, it's missing a pair of dots. Oxygen requires an octet as well. So 2 atoms, 2 lone pairs, we recognize this as bent geometry. Even though it didn't say, I can go back and add. Trigonal planar are always 120 degrees. Tetrahedral, 109. Trigonal planar, 120. Equilateral triangle there. Trigonal pyramid, a little less than 109, so about 107.5 or so. And bent, about 104.5. And again, just remember that it's a little less than the ideal 109. And here's our answer just to compare. We had a trigonal planar, 3 electron domains. We had a tetrahedral, 4 electron domains. Here this carbon is attached to 3 different atoms, trigonal planar. This nitrogen attached to 3 atoms and a lone pair, trigonal pyramid. This oxygen attached to 2 other atoms and also 2 lone pair. We called it bent. I'm going to pause the lesson there. We're going to pick up with section 4, drawing organic molecules. When ready, come on back.